Welcome to a lesson with Dr. Powell. In this video, we're going to take a look at an optimization problem in calculus where we're using derivative information. So you see this beam, or think of this dark line as being a beam and going around a hallway or something. Say this is 1 unit of some kind. This is a half unit. So we want to know how many units this beam should be at worst, in order to, like, what's the worst possible scenario where it actually fit through? What's the longest beam we could actually like slip through and so it doesn't get stuck here in the situation and we're gonna let it depend on this angle theta right here. So we'd like to find a function that we can minimize or maximize, and it should be in terms of theta. Well, let's see. We want to find the maximum beam that would actually work. That's the same thing as the minimum beam that won't work. It kind of coincides. It kind of hits that point right there. It works right there, depending on friction, how it slips. So what we can do is, so we could think of it both in either way. So let's think about a picture of beams that don't work. Now, if a beam doesn't work, it's going to come all the way from this point to this point. So, meaning we can draw some triangles and kind of work with it. That angle's theta, and we have some triangles. Maybe I'll draw this a little bit bigger so you can kind of see. So, so why don't we just do this? And then go like this here. Just make this a little bit bigger. All right, so let's take a look at that. Okay, here we are. So we have this. We have a triangle here. We have a triangle here. Think theta, theta. We want to come up with a formula that represents the length of this, right, in terms of theta. Well, let's see. We know this length is 1 right here. Hey, from our triangles, if you looked at some of my videos on those, we have of defining 6 trigonometric functions using similar triangles. If we have theta 1, what's the definition of this side length right here and this side length? This is cotangent theta. This is cosecant theta. We automatically know that this, we're very close to our formula, is cosecant theta. What about this length right here? What would that be? So theta, we know this is a half. Okay, so if we kind of look at there's one of the defining triangles that has a 1 right next to the angle theta. And for that one, you have tangent and secant. So, but this has a 1/2 instead of a 1, so you have to multiply everything by a half. By a half. Okay, so this side length right here is actually 1/2 secant theta. So we really have our formula for the length of the beam. It's 1/2 secant theta plus cosecant theta. And we want to find the minimum of such thing, because this is like the minimum situation that doesn't work, where you're going all the way to here, and you're hitting that corner. Okay, so to do that, we're going to take a derivative, L prime of theta. And the derivative of secant is secant tangent. So 1/2 secant theta tangent theta. And then cosecant, the derivative of that is negative cosecant theta cotangent theta. And we'd like to know where this is equal to 0. All right, it's going to be well defined. Let's see. Well, if theta is staying between, within a right triangle in this situation between 0 and 90, or 0 and pi halves for radians, if it stays strictly between there, so strictly bigger than 0 and strictly less than pi halves, it's always going to be well defined. So we really want to find out where this is equal to 0 in that range, in that that range of values of theta that are acceptable. Okay, so this is like a trigonometric equation. And if you looked at my videos on solving equations of trigonometric equations, what I do is I think of these as x and y values on a unit circle. I can think of this tangent as being like y over x. I just going to rewrite everything as y's over x's. And this is being 1 over x. And you have 1/2 times minus, and then think of that as cosecant as being like 1 over sine or 1 over y, and cotangent as being x over y equaling 0. Okay, now notice you have your common denominator that you would like will actually end up being, if you put this in the factored fraction form, would be 2x squared y squared. So to get this common denominator, this fraction top and bottom, you have to multiply y squared to top and bottom. This one, you'd have to multiply 2x squared to top and bottom. 2x squared, 2x squared. Then in that process, notice you end up getting, let's just look at the numerator, because the numerator being 0 is the important thing. Denominator, I mean, that just makes restrictions. But really, a fraction is equal to 0 when the numerator is 0 and the denominator is non-zero. So the top will look like y cubed minus 2x cubed, and that's equal to 0. So really, we've simplified to this, and we're on the unit circle. Okay, so this is the same thing as saying y cubed is equal to 2x cubed. You could divide by x cubed, and you could think of this as y over x. Now, I kind of like that. If you can get that something like that going on, that's great. Because really, cube root of 2, because y over x is like the tangent of, you can go back to theta if you want. Tangent of theta is equal to the cube root of 2. So, at least in our situation, taking the inverse, or tangent inverse of cube root of 2 will win, will give us the theta that we want. This will be the value of theta. Now, does it represent a, will we actually be minimizing this? I mean, I suppose what we could do is we could take a second derivative of this situation and keep going, and then plug this in and see if you get a, we want to get a positive number for concavity. That'd probably be the best way if you needed to look at that. I'll forego that in this particular video, but at least we got to the critical point. And again, how do we check it? Concavity, looking at the second derivative. So you look at the second derivative, you work it out, and then you plug that in. And I said I would forego it, but maybe, I guess we could look at it slightly if you want. I mean, what would we have to do here if we wanted to take that? We would need to take a derivative of this using a product rule or boxing method or something like that. Derivative of secant is secant, so we'd have a 1/2 secant theta tangent theta, but then, so derivative of this part, but then this part's still multiplied on, so I'll put a little square right there. And then we have plus another 1/2 secant theta. Then we won't be taking a derivative of that, but we'll take a derivative of the tangent, which is secant squared. That'll make a secant cubed right there. Okay, so we took the derivative of that part. Now, now a derivative of the next part, right here, we would get by doing what? Derivative of cosecant is, but then with the negative, become positive. So positive cosecant, so cosecant theta, cotangent theta, because it's positive because of there was a negative there, and then just times cotangent again, because we're not taking derivative of that, just using product rule, boxing method, so cotangent squared. Now we're going to take a derivative of the next part, cotangent, which the negative will interact with that negative to make a positive. So plus, and then we have what? Cotangent, plus, and then we're multiplying by just cosecant, because we haven't taken a derivative of that. That's just still hanging out, times derivative of that, which is cosecant, negative cosecant squared, but the negative's already been changed to positive, so cosecant squared times cosecant is just cosecant cubed. Now, realize, see this tangent inverse of cube root of 2? I mean, where does this angle live? This angle lives in the first quadrant. Now, secant, tangent, and all of these guys, cosecant, every single one of these is actually positive in the first quadrant. And we have a plus, meaning the whole thing is positive. So we can just automatically say, hey, by virtue of this being in the first quadrant, I mean, why is this in the first quadrant? Maybe we should review that. Well, inverse tangent. Inverse tangent tells you an angle strictly between negative pi halves and pi halves, or if you want to, if you're looking at degrees, negative 90 and 90. And it only outputs negative numbers if you're inputting a negative number. So if you're inputting a positive, it's going to output positive angles. Hey, it's between 0 and pi halves. That's in the first quadrant. And if all trig functions give you positive values in the first quadrant, look, this whole slew of things is positive, this sum and products and all that. So we're actually good to go. So I actually did it, I guess. I mean, I didn't exactly plug in, but that's enough just to explain that and say, oh my goodness, yeah, it does work. Okay, it is concave up there at this point. That's where the derivative is equal to 0. We're good to go. Okay, so it is a, so we do know it is a minimum. So I guess it wasn't too bad. I mean, maybe it looked bad, but it really works out. So we do get a minimum. Now, maybe the question is, what is the minimum length then, if we got that, right? Well, what do? We got to plug in this point right here plugged into the function, the length function. So L of that should give us that length. Let's look at that for a minute. So L of the inverse tangent of the cube root of 2, this is an angle. Now, it's worth not just leaving it like that, because as we plug it in, it actually makes it a little simpler to figure out what the length is as a number. So what we do is we have 1/2 times the secant of this angle, tangent inverse of cube root of 2. And we're going to discuss how this is actually simpler than it looks. It looks terrible, but it's really not that bad. Plus cosecant of inverse tangent of cube root of 2. So let's start off right here with the secant. So the secant, now realize that we're computing the secant and the cosecant of the same angle. And secant and cosecant, let's see, yeah, okay, of the same angle. All right. Okay, so let's just go for that right now. All right, so secant of this angle, well, we have a we can build a triangle that has this as an angle. How do we do that? Let's do that. A triangle has that as an angle. So the angle would be this, tangent inverse of cube root of 2. Now what's special about that? And maybe make that a little bit more clear. Cube root of 2. Special of this is what happens when you take the tangent of this. Don't you get cube root of 2? Yeah, so let's just think, oh, tangent is like this opposite divided by adjacent, so we can think cube root of 2 and 1. Ah, what's the hypotenuse? Well, this squared plus that squared rooted. So square root of 1. Now, what's a square of this? I mean, you know what? If you do cube root of 2 times cube root of 2, the two 2's can come on the inside, 2 times 2. It'd be cube root of 4. Or you could think of this as like 2 to the 1/3 power, and if you square it, the 2 and the 1/3 multiply together, so 2 to the 2/3 power. And then you can think 2, 2, and then do a 1/3. So like 4 to the 1/3, well, however you want to think about it. But but cube root of plus, and you can do cube root of 4. Okay, so this side length right here, 1 square root of that's going to be that length. All right, so we have a nice triangle. We can compute let's compute these angles on them. We're going to compute the Okay, so what do we need to compute? We need the secant of that angle and the cosecant. So what's the secant of this angle in this triangle? Well, secant is always the hypotenuse divided by that side. In fact, remember, this is tangent of the angle. This is secant of the angle. That is secant of the angle. We just computed it by getting the hypotenuse, right? So really, we have 1/2 times that. So we can build this. Maybe I'll, just for kicks, because I'm running out of room, I'll just write it up here. 1/2 times that thing. 1 plus the cube root of 4. Okay. So that gives me my secant. What's the cosecant? So now cosecant is the hypotenuse if what? If this side length were 1. So to make it 1, you just divide everything by 1. If you divide everything, or by cube root of 2, divide everything by cube root of 2, then this side length would be 1. And then automatically, what does that do? That forces this side to be the cosecant, and that's the cotangent. So the cosecant would be this. So then we have just plus that. So plus, then again, 1 plus cube root of 4 this time, but all divided by the cube root of 2. Of course, you could factor whatever, do whatever you want with this expression, but this actually gives you the length. Notice how we got the length without even using a calculator to this point. We have an expression that we could plug in to get a decimal that would give us that length, but at least we computed that length. So I hope this example gives you some practice with a number of tools and different things that you can do, finding formulas for theta using kind of like these similar triangle ideas, and even how to plug in angles that look like an inverse of something. Thinking about inverse trig functions, looking at the second derivative for concavity and all of that, solving trigonometric equations. There's a lot of stuff there. Hopefully that gives you a little, you can glean something from it, and it'll help you in what you're doing. Thanks for watching.